off, our project is MiniDEX. My name is Jonathan Shanowski. This is Raksha and Cole Banta. Just to kind of start off our project, we're going to give a little bit of history to our project, kind of why we chose it, and why it's nifty. So I just have fun.
So just a little background. In the 1970s, the U.S. government commissioned a company called MiniDEX, Inc., which is based in Anaheim, to manufacture an omnidirectional symbiotic autonomous system as a research vehicle, based on the idea that a walker can outperform a roller using an alternating tripod. And just some initial specs, it has 6 legs using the tripod gate. It weighs about 370 pounds. It's 5.5 feet tall, and the material is made out of aircraft-grade aluminum and steel, and it has a fixed sensor array, and each leg has a lifting capacity of 450 pounds, so that's about a total of 900 pounds of lifting capacity.
So before I kind of go into the whole project goal, I kind of wanted to highlight this project because while everyone's kind of looking for projects to kind of choose and what they want to do, we actually happened to stumble into the machine shop and we saw this kind of hiding in the corner, or actually, sorry, the original one. Basically saw that hiding in the corner collecting dust, and we was like, okay, us being real big sci-fi nerds, we was like, oh, this is perfect. Let's see if we can do something with this. So we actually has like a little side project, a little historical kind of restoration on it, but the main project goal was essentially to make our own, about 80% the size, but also kind of maintain the same geometry of the original ODEX one, but just kind of update electronics, because since it was from the 1970s, there's been just outrageous amounts of progress done on electronics and programming, all that fun stuff. But basically, we wanted to make the project kind of do the same goal that it initially had as well, being a symbiotic system. Basically do anti-fatigue systems, so like help you carry things around. Kind of like a pipe dream was to have it follow you around like campus, just kind of help you carry your backpack, that sort of thing. But also the biggest goal is to basically be a legacy project, for it to be a research platform for more students to get more involved in robotics on campus, to do stuff like robotic design and manufacturing. The biggest thing, motor synchronization, which was very educational, and also sensor mapping. Like I said previously, scaled down version of the electronics, all that fun stuff, obstacle avoidance. Another big thing is making it modular and expandable, so more people can add their own little tidbits to it, just to be like, oh, I want to add a grabber, I want to expand upon it, basically build on it easily.
And so our DEX, it stands about 4.4 feet, and sitting down it's about 2.4 feet. And it weighs 53 pounds, and we made it out of furniture-grade Baltic Bridge plywood, as well as there's a bunch of threaded steel rods, and we also did a lot of 3D printing with ABS plastic, and it has 6 legs. We use 3 motors per leg, which is 18 motors in total. There's a rotating sensor array, and there's over 250 feet of electrical wiring, and 46 custom designed and over 400 manufactured parts in the robot itself. So.
And then just kind of go off the design bit itself too. When we first started the project, we to kind of maintain the same geometry, we actually did the full CAD of the original ODEX for historical purposes, but also to be able to maintain the same mechanical advantage. We did all the CAD ourselves. This is the assembly of pretty much the entire thing. As Raksha previously said, it has something like 426 parts to it. About 46 of those are unique parts, so we had to make all those. And these next few slides obviously go into the manufacturing process. So for the first semester, as I'm sure a lot of you guys saw, we just kind of started off with a leg. We had to do a lot of prototyping just to make sure it actually worked. We didn't want to invest a bunch of time into it, making all the stuff, wasting a lot of money if it didn't work. So we actually, one of our local club members, his dad has a full machine shop, and we were able to actually use a CNC mill and lathe to do a lot of the prototyping. However, that took a lot of time. It took about like 16 or 18 hours to produce one leg. So we quickly changed to, there's a local makerspace that actually has a laser cutter, which made it incredibly easy. Just basically load everything up, transfer it all over to G-code, and press a button and it kind of goes. Also, kind of to elaborate more on that as well, we did have to modify a lot of the original design, because since it was made out of plywood, we had to kind of change to the design, the machinery we had at the time. Then we also used a 3D printer. to do a lot of the more custom, more complex parts. So this is the assembly. This was about maybe a week ago before we actually attached the head. We actually had it on a engine hoist to keep it all elevated and able to basically play around with the legs, try different types of gates, try a bunch of different things. And then this is with its head, and as you guys can see, that's the kind of final product right now. And yeah, come on that way.
Okay, so as I said before, 18 motors in total. Each motor has 2 limit switches, so that's 36 limit switches in total. We used 2 IR sensors, 2 rangefinders, 4 ultrasonic sensors, 1 stepper motor, and 7 stackable shields, 7 batteries, each of 11 volts, 2200 milliamps, and 1 GPIO extender and a Raspberry Pi. And this is, yeah.
So right here is basically a flow chart of how we set everything up. The sensors that are connected to the extender on top of all the shields will send its data to the Pi. The Pi will then relate that information by processing it and sending it to the motor hats, which then will go through the limit switches and control the motors. And we had to have those limit switches there just in case the motors went too far past their access points and just cut off the power so they didn't keep turning in the same spot. And so this is the design that we came up with. We 3D printed this case so that we could have fans cooling down our Raspberry Pi, which is right there. We have 7 motor shields stacked up on top of each other, and we're able to access them through I2C addressing. We just attached a GPIO pinout board on top of that as well on these extra pins, and that way we were able to have 3 layers of 40 pins for the Raspberry Pi pinouts. And then we had 3 motors connected to each board and went out to each leg so we can control each leg individually.
And just to kind of touch on this a little bit more too, is that what's really nice about the motor shields that we found out is that they had their own unique addressing. So it made programming a lot easier. You could do a lot more library calls, a lot more methods, just kind of being like, hey, for this motor shield, run this X, Y, Z kind of thing. They made it very, very convenient and also very simple. This is just to kind of go a bit more into motor wiring. One of the big reasons why we have so many limit switches is to kind of restrict any possible harm that might come to the robot, just in case it exceeds some form of threshold. So if it decides it doesn't calculate right and it tries to swing too much, basically it will prevent it from actually going too far and breaking itself. So we just have this pretty much set up for each and every leg. We also have it so that each leg is powered separately, so you can kind of keep an eye on making sure the voltage is good, and also kind of add more things to it if you want to add something for just one leg instead of having to kind of tie into the whole system. You can just kind of keep it all localized.
And here you can see that we 3D printed this housing for the sensors. We have 2 ultrasonics, one facing forward and one looking down. Along with that guy, we have an IR, and then up top we have a long range finder. We found that we could get accurately about 350 centimeters with the ultrasonics, so those were our most dependable. And then we only got about 80 centimeters with the IR, so we just utilized that for what's right in front of the bot. And then the long-range ultrasonic finder we use for bit mapping and detecting things at a greater distance to kind of plan out your path of travel rather than just having to stop when it detects it.
And that's actually one of the issues that we ended up having with it, is that I'm kind of happy with the initial design. We try to keep it modular so you can kind of switch out with which sensors you want. You can actually take out this little front panel, change out the sensors, and redesign it instead of having to 3D print the entire new thing. But we actually were going to do a lot more IR sensors, but the IR sensors we had, like I said, didn't perform as much as we wanted, so we kind of went back to the drawing board and added more ultrasonic because those were a lot more reliable. And then this little GIF right here just shows the kind of step pattern the motor head kind of goes through, just to make sure it's kind of passively obstacle avoidance, being basically making note of what things are where, and it can just kind of store it locally and not have to worry about too much processing over that.
And then, so we wrote 2 different sets of code, one for being just this autonomous navigation. So basically, you just have your libraries up top. You set up the pins for in and out and assign them for the Raspberry Pi. This is just a call functions for the long range finder right here by itself. Does the processing for what it's seeing and turns it into an actual readable value. And then right here, it's starting to call upon either turning left or right, and what it does when it goes left or right, it starts at an initial count of 0, and then when it detects something, it'll go to 60 degrees to the right. If there's something there, it'll go 120 degrees to the left. If there's something there, it'll go 180 degrees to the right, and so forth, and so on, so that it checks to see where is a clear path for it to go. Next slide. And then it just continues doing that. This is the forward call, the right's up top. And then here is just more setting out inputs and outs. And then over here is, this is for the first ultrasonic sensor that continues to the second ultrasonic sensor, because we have 4 total on the bot. Just processing the data and turns it into a value that you can read actually on the screen. So that's the second, third, and fourth ultrasonic sensor. And then here, depending on where the stepper count is, it'll go to the next one, and it'll either turn left or right based on that and a flag count that it keeps when it detects something in front of it. So we have it set to about 300 centimeters for the ultrasonic sensors, and everything seems to work pretty good when we have it all hooked up. The second one that we wrote is, a lot of it's the same. We still call the same libraries, and we have the same pinouts, and then we do the same processing, but the only thing that's different is that when it performs, when it sees the data and processes it and sends it to the motors, it acts differently. So for this code, it's, instead of just looking for a way without an obstacle in front of it, it'll actually process where the obstacle is, find a direct route either to the right or left of it where it's clear to walk, and then walk around it, get back on its original path of travel, and then keep going to the obstacle. It's just more of that code. One more. And then this is the code that we wrote. So with Python, you can call upon other scripts as long as they're in the same file. So we wrote scripts for at 60, 120, 0, 180, 240, and 300 degrees. So the head could just turn, and the legs wouldn't have to actually turn with it. It could just walk in that direction. So we wrote a script for each and every direction that it could walk, and it would just call upon it based on that count that it kept track.
And then another thing to kind of add to that too is that we initially were hoping to do PyPy communication just to make sure that since it is running a bunch of different things in the background, we didn't want to bog down the response rate. But unfortunately, like one of the other bigger teams stated, we can't really do socket connections with the PyPy, so we actually just kind of put it all in one, and it's much larger part that actually handles it pretty fine. So that definitely helped a lot too. Just to kind of touch a bit more also on modularity. Since one of the main kind of goals of this project is for more students to kind of get involved in robotics and also kind of build up on it, with the chassis we've made it so that you can expand with components that has a lot of space that you can kind of add to it, as well as the hardware itself. It's very modular. We made sure to get the stackable motor shields. You can get something like 32 of those shields. We have 7, so we can really kind of go crazy with it. Same thing with the GPIO extenders. You can just keep on adding more to it. And then also same thing with the independent powering to add more kind of peripherals on there. So here's some of the demos that we did earlier this week. This is just kind of, this one over here is just controlling the pitch. And just showing, just kind of going through different kind of gates that we came up with. And the same thing with this one. This is just, with the 3 motors, they basically control elevation, yaw, and pitch. With that kind of combination, you can come up with some kind of complex movements. And like Cole kind of suggested too, you can really just kind of go off in any direction that you choose. So if an object is directly in front of you, you don't have to worry about kind of veering off. You can just go out and notice and change direction. Uh-oh. It's because I didn't log in. Yeah, let me log in. Don't mind that, this will launch faster. So this is just us doing the first test. Like I had previously stated, we try to keep it elevated just to really allow free movement and not have to worry about things breaking. So this is just kind of starting off, the initial movement is actually based off of what's called a tripod gait, which is a movement that a lot of insects use. So basically, 3 legs move opposite of each other. So in this case, 3 rise up, move, get put down. Same thing with the other ones, rise up, moving it down. One that actually improvements that I'd like actually to touch on too is, unfortunately, the motors that we had were a little bit smaller than what we initially wanted, so the speed of the leg elevation can be improved upon. As you can see, it's a little slow. To be completely honest though, for the pitch and this, for the yaw, perfectly fine. Just a note of the elevation, a bit more power, a bit more oomph. So we can go to the next one. Okay, so this was the most terrifying part, actually having it walk. Feel free to play it now. So we were kind of dreading this moment of will it balance? You kind of have to jump off and just kind of like let it go on its own. If it falls kind of thing. So this is one of our first initial tests, and luckily it did actually balance pretty well. Was able to support itself, but it is, like I said, a little bit slow just because the elevation control is just not there. But it does, like I said, support itself. But another thing that can be improved upon is also integrating the IMU. So an IMU is basically an inertial measurement unit. That allows it to have like a gyroscope to kind of balance itself and make sure that was one of the biggest things, is that we wanted to make sure it didn't kind of topple over itself, because if it falls, that could be bad. Okay, it's that. Also, in a similar one of these tests, like I said, we did this maybe like a week ago or so, or over the past few days. It has a lot of issues with vibration. It was actually, at some point, some wires must have crossed, and it actually fried two or three of our motor shields, and actually Raspberry Pi as well. So we actually are getting some more motor shields in the mail that we're actually getting probably today, and we're going to reinstall those so we can continue testing. And so this is just a slide on what can be improved upon. Like I said, the biggest thing that this could be used for is motor synchronization and improving the gait. There's a lot of things that you can do with it just to make it walk a lot faster, improve the type of walking it can do, as well as the sensor mapping. Currently, there's a pretty basic sensor mapping using just ultrasonic, but there's also a lot of expansion that can be done into like OpenCV using like PyCams, or also LiDAR, just for more sensor mapping. So you don't have to really worry about too much. Also, improved system organization. There's a lot of wires in this thing, and also making sure they kind of stay out of the gears and don't fry something is definitely something that can be improved upon.
We ended up like zip tying a lot of cables together just so they wouldn't like cross, and that was after we fried our shield. And so we ended up zip tying a lot of stuff, or a lot of wires, so that they wouldn't cross.
And I'm not sure if, I guess you see, I should probably actually take the camera too, just to kind of demonstrate. How do you put it on?
Yeah.
Aha, look at that, that's pretty nifty. Let's see if it's long enough. We good?
Yeah.
But as you guys can see, there's a lot of room for expansion, a lot of crazy wires going everywhere. These motors actually have encoders on them as well to kind of improve upon how far things can step and just all that fun stuff, but it's a bit of a mess. Also down there's a bit of a mess too. But yeah, it's a lot of wires. And then another thing is just the mechanics. Since we did have a bit of a budget, or a little bit of a lower budget, relatively, we had to make it out of wood. We tried to implement a lot of metal parts as well, but there's definitely a lot of expansion that can be done in metal. We found a way to use 3D printed gears, but metal gears would definitely be a lot better. We wouldn't have to worry about too much slipping or any of those issues. Like I said, larger motors, and maybe also including a lot more of the shadowing. But the biggest thing is just kind of adding more onto it, adding more attachments, and kind of having fun with it. Let's see if we can go to the next one. Okay.
So just the basic cost breakdown. We spent about $650 for the actual manufacturing of the robot, and then $475 on total 19 motors, and $320 for the batteries, and $457 for the components, so a total of $1902 or $1,902. Our budget was, what was it?
Initially it was like 18,
18,
and then it got bumped up to about 2,000-ish.
And so.
So luckily, kind of under budget. But yeah, thank you very much. Any possible questions?